This is the video for heat mass, and this is the homework problems for homework number 6. So in this first problem, we were trying to find the heat transfer coefficient of wings on an airplane, and we were given all these values and data, and we had to go to our table and look up our properties to find our Prandtl number and these other values. So as we plug, this was a pretty straightforward problem. You just plug it in order to find your rho and your density, and then you manipulate this equation here to find your heat transfer value. You plug your values in, and then you're able to find a heat transfer coefficient of 89.6, which was a pretty straightforward problem. The next one was a little more in depth, as we're trying to find the velocity of that a free stream needed to be provided at in order to keep transformers cool. So we were given all of our values once again, and then we're looking for a velocity, and we're able to assume steady state, and we're able to get some other critical numbers for a Reynolds number. And then in order to solve this, we had to get different areas for fins and unfinned. Then we had to get it in for our Q value, or you manipulate this to get our H, and then we're getting our Nessel number, which in turn gives you your Reynolds, which in turn can be manipulated to get your velocity. In the third problem, we're looking to find the length and a surface temperature for a household heating water condition. So we just take all of our knowns again, our assumptions, then we go and look up all our properties once again in order to solve this problem all the way through. So the first equation we start with is regular MCP delta T in order to get Q, and then our length is our Q total over Q given in the problem. And then we were able to manipulate all of our known equations again to get a velocity and a Reynolds number in turn from that. And then once again, we are able to use Reynolds number and the Prandtl number given in the tables to get a Nusselt number. And then this Nusselt number can be manipulated to get an H value, and the H value can be manipulated to get a Q. And then you just keep going straight forward to get a heat flux, and then you can manipulate a heat flux in order to get the surface temperature. And the length was given previously before solved for in the problem with that simple value here. The next problem was determining heat loss, but there was a couple tricks as this had radiation and a couple other things involved in it. So once again, the knowns, the assumptions, steady state, and air is an ideal gas, and we're at 1 atm. We go look up our properties, and then we're able to find our critical length, our area of the top, and the area of the side of the specific dimensions we're looking at. Then we go and find our Reynolds number, and then once again we go to find our Nusselt number, and then the Nusselt number helps us find our heat transfer coefficient. And then once we get that, we're able to plug it into this equation, solving with the area at the top, which is 6.55. Then we have to repeat the problem to find our Reynolds number and our new Nusselt number for the area of the side to get a new Nusselt number, get this area. And then the Q of radiation is just simple, straightforward from the previous chapters, and that gives you this, and then you're able to get a fraction conversion of the heat loss. Finally, this last problem was looking for more heat transfer coefficients relating to a square plate. So we're at laminar conditions, so we just get our values, then our assumptions as a steady state, and then once again look up our properties. And then there's these equations to look for H star Fg and Hx, which is the distance of the heat transfer coefficient. And then you're able to plug in at 0.1 and 0.2 regarding which distances you want of the plate. As far as this week, the confusion was just a little bit of how many equations we had, especially with Nusselt number, Prandtl number, and Reynolds number.